Hi, I'm Yuqing from the University of Waterloo. I will talk about the work done with Yuanjun, and Stefano from Amazon AWS AI. The topic is regression bugs are in your model. We introduce the regression concept from software engineering and computer vision to natural language processing. It happens when you update the system to a new version. Let's first look at the problem setting. We have an old system and we want to update it into a new one. Say update from an animal-based system to a bird-based system. We want to upgrade because the new system has better performance. Say the bird-based system improves accuracy from 70% to 85%. We might think the new system just fixed some of the errors in the old system, so it acquires a better performance. However, the actual case is the new system will fix more errors, but will also introduce new errors. These newly introduced errors are what we call the regression errors. But why do we care about regression errors? Imagine you just upgraded your phone. You will be happy to see some of the new features, but you will be more frustrated if some of the features won't function anymore. And you might refuse the future updates or even refuse to buy a new phone from the same company. As a service provider, we surely want to improve the overall performance, but we don't want the regression errors to affect the user experience. The predicted cases can be categorized into 4 classes depending on old and new models' behaviors. If the new model makes a correct prediction, we call it a positive case, otherwise negative case. If the old and the new model gives different prediction, we call it a flip case, otherwise a no-flip case. We measure the regression error based on a regression set. The portion of the negative flip in the set is defined as a regression error, namely negative flip rate, which also means the portion of cases where the older system provides correct prediction while the new system does not. In this work, we focus on classification tasks in NLP and take the glue dataset as our benchmark. Here we select the 2 paraphrase detection tasks, MRPC and QQP for example. Say we are updating a bird-based model to a better version. Another bird-based fine-tuned with different random seed, a bird large, or a robot-based model. In the table, we show both accuracy and the negative flip rate defined as before. We find that minor changes, such as the random seeds, can introduce a significant regression. And also, negative flip rates are often much higher than the accuracy gains. This implies reducing error rate alone does not ensure the decrease in the regression. The regression-free model updates first come into sight in Xiong et al. For image retrieval tasks. Later, Yang et al. Formalize the problem and explore solutions on image classification tasks. They suggest negative flip as a measurement and propose a specialized knowledge distillation along with ensemble as methods to reduce regression. We are the first to investigate the model update regression problem in NLP tasks. We might also relate the regression problem to the domain drifting, or meta-learning, or transfer learning. However, the regression problem differs from them in that the underlying tasks or datasets stay unchanged, and so we only focus on the model update. In the computer vision, distillation and ensemble are proven to be helpful in reducing regression. Let's first justify why knowledge distillation can help. The regression-free condition can be considered as an additional constraint when optimizing the original problem. After applying Lagrangian relaxation to the constraint optimization problem, we can convert the hard constraint into a term called the constraint violation penalty term. The constraint violation penalty term is measured by the distance of the two models on negative flip cases. This new form is similar to a joint learning of the original task and a modified knowledge distillation. One thing we should notice is that here we only add the penalty on the regress cases instead of all of the cases as in normal knowledge distillation. We provide three options of penalty term. First, distribution distance after the classifier. Second, the L2 norm of the backbone representation. Third, the sum of distance of all layers representation when we are upgrading to a similar architecture. In this experiment, we update from BirdBase to BirdBase or BirdLarge on the MRPC dataset. Overall, adding the penalty at the distribution level produces consistent regression reduction across different setups. In the updating to BirdBase, deeper representation alignment could help. Another method to deal with the regression problem is ensemble. Ensemble can reduce the model variance, which is part of the source of regression. We introduce ensemble 5 new models with different random seeds through voting as a baseline. To understand how ensemble works under the regression setting, we fine-tuned with different random seeds to get 20 old BirdBase models, 20 new single models, and 20 ensemble models. We compared with each old-new model pairs to get the distribution of the regressions as shown in the figure on the left. We find that the ensemble can not only bring down negative flip rate, but also can reduce its variance. We conjecture a model fine-tuned with different random seeds could rely on different sets of patterns for prediction, leading to behavior difference and regression. Ensemble aggregates the distinct behaviors from individual models, increase the compatibility with each individual models on average. We further select the centric model, which is a single new model, by choosing the one with the lowest average regression when updating from other new single models. Results shows that the centric model achieved a substantial reduction in negative flip rate and comparable with the ensemble models. Here, we compare the two methods across the blue benchmark. We show the update from BirdBase to BirdLarge here. Results on each dataset is shown as a group of 3 bars. From left to right, they are the result of distillation, baseline, and ensemble respectively. Blue and green parts together represent the accuracy. The red part represents the negative flip rate. Overall, distillation can greatly reduce regression. Ensemble sometimes also works well. To further understand where the regression happens and how the above method contributes to reducing regression, we leverage the checklist behavior testing and construct regression tests. For example, to test the capability of dealing with semantic role labels when there is an asymmetry order verb in paraphrase detection, the system will automatically select asymmetry verbs and swap the 2 persons around it. The model is required to label the 2 sentences as not paraphrases. Here, we show the results of the error rate in behavior regression tests compared with a fixed old model. The blue part represents the baseline. Distillation in red has a relatively low error rate, which means it can effectively reduce regressions. This demonstrates that adding the distillation reduces the regression through actual aligning new model's behavior with the old model. For the ensemble in green, we observe that it can only reduce regression on a handful of capabilities. Without involving the old model in the progress, ensemble cannot successfully reduce the regression on certain behavior tests when updating from another distinct model. To conclude, in this work, we show that the model update regression occurs across tasks in NLP. We formulate the regression-free model update into a constraint optimization problem and further reduce it into a relaxed form which can be approximately optimized through knowledge distillation training. We also explore the model ensemble as another solution. We analyze the source of regression through linguistic behavior testing, and we find that distillation can effectively reduce regression in both standard datasets and behavior tests.